Yeah, good morning, Victor. How are you?
Science of today, the technology with some
Good morning.
a very warm and pleasant morning to one and all. Myself, Poonam Bajoria, take the golden opportunity to welcome you all to the distinguished lecture on SiC fabrication in a silicon fab. This section, ETS Society, IEEE Nanotechnology Council Student Branch Chapter IIT Indore, and IEEE Sensors Council Student Branch Chapter IIT Indore. It's a pleasure for us to have Sir Victor Veliadis, Executive Director and CTO, Power America, Professor, Department of Electrical and Computer Science Engineering, North Carolina State University. Let me give a short, brief Professor Victor is an executive manufacturing USA Institute of Industries, universities, and national labs, accelerating commercialization of next generation silicon carbide and graphite parts in the $156 million, which strategically allocated to over an industry and university work development and job creation. His part trained 430 full-time University of Institute. In 2024, Professor Veliadis was U.S. Department of Commerce. 400 keynote tutorial invited presentation. Keynotes ICSC, CE, EE, ECPE, WS, WIPDA, CAE, IECO, and EDA. He has taught conductor device in United States.
Hello, sir. Am I audible?
Yes, you are. I'm sorry, I
So,
just lost.
yes, sir. So we
So
were.
are we ready to?
Yes, sir. Poonam has introduced you. So kindly share your slides, and the stage is yours, sir. So
Thank
unfortunately,
you.
we had some technical issues, so we got a network outage.
Okay, so please let me know if you can see my screen and if you can hear me well.
Yes, sir. It is full
Okay.
screen, and we can hear you.
Okay, so thank you very much for the introduction, and it gives me joy to be presenting to you. What I will talk about today is fabricating silicon carbide devices in a silicon fab. So before I proceed, I have to give some slides about the Electron Device Society. And the Electron Device Society works in all type of devices, including the semiconductors, which is the lecture we're going to hear about today. And a membership in the Electric Device Society helps with education. There are avenues for publication. You can network with your colleagues. There are awards that you can receive, leadership opportunities, projects that are running, and uh, if you're interested more on the Electron Device Society, please look at this site right here. They're on different avenues, including Facebook and LinkedIn and Twitter. And join today. That's the last slide I'm obliged to give you. So with that, I would like to start my talk. And what I will talk about today is silicon carbide devices. But before we talk about the fabrication of the devices, let's spend a few minutes to understand what makes silicon carbide as well as GaN excellent material for power devices. So if you look at this graph, this spider graph here, you can see silicon carbide material properties are denoted in red, gallium nitride is in orange, and silicon properties are in blue. So you can see that the electrical breakdown field, the critical field in silicon carbide and GaN, is about 10 times higher than that of silicon. The second thing I would like you to note is that the wide band gap of silicon carbide and GaN is 3 times higher than that of silicon. So having a wide band gap means that at room temperature, you have very few excited carriers. So in silicon, it's 10 to the 10th at room temperature. In silicon carbide, it's 10 to the minus 9th, so 19 orders of magnitude lower. So the fact that you have a wide band gap means that at room temperature, you have very few excited carriers. That means that your leakage is very low, and it also means you can operate at higher temperatures. So let's see what the wide band gap and the large electric breakdown field mean in terms of making devices. So if you look at this schematic here, this layer
we have mentioned so far, and they are close set we have mentioned. So therefore, so the previously what I have mentioned here.
Okay, I can continue, correct?
Yes, sir.
Okay, thank you. Yeah. So if you look at a typical vertical power device, it has this thick layer here that holds the high voltage, and this is a MOSFET, and this layer is the drift layer. Okay, and it has a certain thickness of Wn. So if you want to make a device that will withstand a certain voltage, this equation right here gives you the thickness of the device. So you can see that the thickness is inversely proportional to the critical electric field, which is this value right here. So if your critical electric field is 10 times higher, as it is compared to silicon, then the thickness of your device for the same voltage capability becomes 10 times thinner. If you look at the resistance of this thick layer, which for high voltage devices is the major contribution to resistance, you can see that it's inversely proportional to the third power of the critical electric field. So if the critical electric field of your material is 10 times higher than silicon, then this drops the resistance by 1,000 times. So we have large band gap and large critical electric field in silicon carbide as well as GaN, and that allows for high voltage devices with thinner layers. So the fact that you have a thinner layer for the same voltage capability means that you have low resistance and therefore lower conduction losses. The fact that you have the large band gap, as I mentioned before, means that your leakage is very low at room temperature, very few carriers excited. And also, it means that you can operate at higher temperatures. And the fact that you now have thinner layers and lower resistance means that you have a smaller form factor that reduces capacitance. And this is critical because it means you can operate at higher frequency, which minimize the size of the passive components like the inductors and the capacitors and the transformers. And of course, if you look at the high thermal conductivity of silicon carbide, which is shown here, it's more than twice that of silicon and gallium nitride. The large thermal conductivity means you can dissipate heat more efficiently, so therefore your thermal management becomes simplified. So this is the reason why a lot of work and effort has gone over the last 3 decades into silicon carbide as well as GaN for power devices. So if we look at the devices that are available today for power electronics engineers, they're silicon devices, they're silicon carbide devices, and gallium nitride devices. And the choice of the device has to do with the voltage requirements, the current requirements, the power density requirements. So higher frequency means that the size of the components gets minimized so you can increase the power density. It has to do with the efficiency that your application calls for. Typically, you want the highest efficiency possible, the temperature of operation for your application, and very importantly, the cost. So therefore, if you look at this graph right here, you will see that silicon carbide basically is available at 650, 900, 1.2 kV, 1.7, and 3.3 kV. And these are all products that are available on the market today, while 6.5 and 10 kV devices have been successfully demonstrated. If you look at gallium nitride, it's available in the 100 to 900 volts with some recent results at 1200 volts and even 1700 volts. And of course, silicon is extremely competitive up to 600 volts. So silicon is reliable, it's very rugged, it's very cheap, it's capable of operating at high currents, and there's design legacy, meaning people know how to design with silicon. If you look at silicon carbide right here, it does higher frequency, it's efficient at higher frequencies, it can do high powers. And then if you look at gallium nitride, it can go to even higher frequencies than silicon carbide very efficiently. So there is this 650 volt area, which I call the battleground, because all three, silicon, silicon carbide, and GaN, are extremely competitive. Now, you will notice that there's a 400 volt silicon carbide device that has recently become available from Infineon, and this device is meant for data center applications. Before I proceed further, I would like to introduce the Power America Network. We're a consortium of 93 companies, universities, and national labs with industry across the supply chain, from materials to equipment to the fabrication, the modules, and then the wide bandgap systems. And these are the companies here. And we also work with a number of universities that have very good expertise in silicon carbide and GaN power devices, chips, as well as the power electronics. And we also work with a number of government labs. And the role of Power America is to bring the whole supply chain together and solve pre-competitive problems to accelerate silicon carbide and GaN commercialization. Okay, so why are we talking about silicon carbide? How important is it? Well, it's becoming a big market. If you look at this graph here from Yole, by 2029, silicon carbide is expected to be 26% of all power devices, and GaN is expected to represent 6% of all power devices. So it's going to be more than 1/3 of the market, of the overall market, which is significant. And silicon carbide by 2029 will almost be a $10 billion industry, and about 77% of the silicon carbide devices will go to automotive and mobility applications. Then industrial, like motor drives and power supplies, will have a pretty big chunk. And then there's a small amount of silicon carbide that goes to aerospace applications. So it is a pretty important material, devices, and development. And that's why there's so much work dedicated to silicon carbide. So the first thing we want to know is the substrate. You need a substrate to make silicon carbide devices, and I will do the comparison with silicon. If you look at silicon, you need to go to temperatures of 1500 degrees, and then silicon melts, and then it goes through this necking process that minimizes the defects, and you're able to get large boules in a very short time, and then you can slice those easily into wafers and polish them. This is not the case with silicon carbide. Silicon carbide melts at very high temperatures, so what you need to do is go to 2300 to 2500. The material will not melt, it will sublime. You need a seed crystal to start the growth, and the quality of your wafers, the quality of the boule that you're going to create is dependent on the quality of the seed layer. So it's a much more complicated process, and you also have to saw and polish silicon carbide, the boule, which is very, very difficult because of the hardness of the material. So more labor intensive, higher temperatures, and smaller boules means higher price for the wafers. Now, let's talk about the fabrication of silicon carbide. When you come with a new material, you do not want to reinvent the wheel. So silicon carbide has basically applied all the mature silicon processes that can be successfully transferred to silicon carbide. However, because of the silicon carbide material properties, because of its special properties of its hardness, you need to develop specific fab processes whose parameters must be optimized and qualified. So what are those? When it comes to etching, silicon carbide is inert against chemicals, and only dry etching is possible. So you cannot do the wet etch that's available in silicon, and it's a very hard material. So if you just use resist, which is the common in the silicon world, you're going to be eating away the resist faster than you're etching the silicon carbide. So you need to have the right masking materials. The selectivity is very important, and the right gas mixtures and control in order to get the right sidewall, minimize sidewall roughness and get the right profile. There's also substrate thinning, because the substrate is a very big portion of the resistance of the silicon carbide device. So we want to thin the substrate to reduce that contribution. When it comes to doping, thermal diffusion is not practical in silicon carbide. You have to go to temperatures that are in the 3000 degrees or so, because of the very high melting point of silicon carbide, the low diffusion constant. So doping is done by implantation. You implant a species into silicon carbide, and you have to adjust the dose, the energy, the temperature, the right materials. And then after you're done with implantation, you have to do a post-implantation anneal to basically activate the dopants and recrystallize the wafer. When it comes to metallization, we all know that you've got to have materials with a coefficient of thermal expansion that's matched. So therefore, the metals that you use for silicon carbide have to match the CTE of silicon carbide. Another one is the ohmic contact formation. In silicon, if you put a metal layer, you're going to get an ohmic contact. In the case of silicon carbide, because of the large band gap, if you put metal on silicon carbide, you're getting a Schottky. So if you want a low resistivity ohmic contact, then you have to do certain processings. You have to go to high temperature and do a silicide, and I'll talk about some of these things. The gate oxide, if you're making a MOSFET, then there's an oxide that's interfacing with the silicon carbide, and the interface of the oxide with the silicon carbide, unfortunately, is very poor in terms of roughness and in terms of defects. There are a lot of traps, a lot of defects in that interface, and those compromise your mobility in silicon carbide. So you got to improve the quality of the silicon carbide gate oxide interface. The wafers of silicon carbide, because of its wide band gap, as expected, they're transparent. Silicon wafers, because of the lower band gap, they're opaque. So you need equipment that uses laser beams or optical light that's meant for transparent wafers. So you have to go to the UV range. So you need some special tools, which today are available because of the size of the market. Because silicon carbide is a newer, of course, material, the wafer is not as flat as silicon, and that can create complications in the fab. And then finally, you have to deposit the dielectrics in silicon carbide, because you cannot have a thick thermal oxide, which, by the way, is part of what has made silicon very successful, that you can do a thick thermal oxide, and thermal oxides have very few defects. That's not the case in silicon carbide, so you got to deposit insulation dielectrics. Okay, so having said all that, if you have a silicon fab and you want to fabricate silicon carbide, this is a list of the main tools you need to purchase that are not available in your silicon fab. High temperature implanter, an anneal, where you can basically anneal the wafer after you do the implantation. You need a background tool to thin the substrate to reduce the resistance of the substrate. when it comes to metals, Ti, chrome, tungsten, molybdenum, these metals here are well matched with respect to CTE, coefficient of thermal expansion, with silicon carbide. Depending on how you do the process, you will likely need a laser anneal tool to do silicide, create silicide and anomic contact in the back of the wafer. And then you need tools that basically are compatible with a band gap of silicon carbide in order to do optical inspections and metrology. So the model that has been very successful in the very big silicon carbide growth that we see is to process silicon carbide in a mature, fully depreciated silicon fab. And fully depreciated means that luckily the equipment that does lithography, photolithography in silicon carbide, does not need to be the latest generation. You can take equipment that's 25 years old and it will do the job just fine. So to process silicon carbide in a silicon fab, you need to buy tools, which basically in today's prices, this is probably going to be maybe $40 million. And then with that relatively small capital investment, remember, it's not in the billions of dollars that you need to spend to make devices of the latest node in silicon. What you do then, you have the silicon production, you're adding silicon carbide wafers, so that creates extra capacity that will help you maximize the fab utilization. And then because you're fabricating silicon carbide devices side to side with silicon, then you have all the production, all the wafer production, basically helping you to get to economies of scale and reduce silicon carbide manufacturing cost. And that has been a very successful model. Now, if you look at the fabrication infrastructure, there are the IDMs, integrated device manufacturers, like, for example, Intel. The manufacture, design, do the intellectual property, and market the devices. There are foundries, and basically foundries will only do the manufacturing. You go and you design to their design rules, and they just manufacture. So it's your design, it's your IP, and then you take the devices and you market them. In that model, there are fabless companies. Fabless companies are companies that do design, develop the intellectual property, market their devices, but do not have a fab. So it's pretty affordable to buy a computer and put the right software, design devices. That's not very expensive, but then finding $200 million to build a fab, that's very expensive. So there are a lot of companies where they do the design and develop the IT, and then they do the manufacturing at these foundries. They go to foundries which only do manufacturing. They don't do design type of work. And an example of a fabless company that everybody knows is Apple. Okay, and then there are design houses which basically do design and develop some IP for the purpose of licensing that technology. So that's the mature silicon world. If you look at silicon carbide IDMs, there's Wolfspeed in the United States, Microchip, and onsemi, big companies that make silicon carbide. And in the case of silicon carbide fabs, you're competing on the design as well as the process, as well as the way you fabricate the device, which is not the case in silicon. In silicon, you compete on the design alone. And of course, the wafer quality and the supply of wafers is also an issue in silicon carbide because they're expensive and their quality varies. You have foundries, and X-Fab was the first silicon carbide foundry in the world that Power America helped set up in 2015. And these are all fabless players that are in the United States, and they went to X-Fab to make devices. So all these fabless companies, all these companies that did not have access to a fab for silicon carbide, went to X-Fab to make devices. And design houses, these are some examples. The University of NC State, SUNY, and others are design houses. And let's not forget that there are the really big companies that do power devices, Infineon, NST in Europe, as well as Rome in Japan. And of course, there's classic SiC wafer fab that does foundry in the UK. Okay, so the cost, very, very important. You can see that this cost right here, this green line, is the cost for the silicon IGBT. And you can see for silicon carbide, the cost is multiple times that of silicon because, as I mentioned, the wafer is a lot more labor intensive, so more expensive, and also the fabrication has specialized steps for silicon carbide that don't exist in silicon and tend to be more labor intensive and costly. So you will pay more for the device. And these numbers, they might have changed in the last year or so, but relatively speaking, it's about 2 to 3 times the price of silicon. And if you look at this graph right here, anywhere between 40 to 60% of the cost of the device, of the silicon carbide device, comes from the wafer. Because as I mentioned, the process for the wafer is very expensive. You pay maybe $40, $20 to $40 for a silicon wafer. It could be $500, $600 or more for a silicon carbide wafer. So with that, the question is, does it make economic sense to use silicon carbide? And let's look at this example here. This is for a PV inverter. This is for a PV inverter. This is the case of silicon. You can see the total cost right here. And in green is the cost of the semiconductor. And then you can see the cost of the silicon carbide-based inverter solution. The semiconductor costs more than 2 times more, but the overall cost of the inverter is lower. So the question is, how can you pay very little for the semiconductor, okay, and end up with a system that costs more? Or said another way, how do you pay a lot more money for the silicon carbide semiconductor and you end up with a system that's cheaper than that of silicon? And the answer is very, very simple. Silicon carbide is capable of operating efficiently at high frequencies. So while silicon is limited to 16 kilohertz, silicon carbide can operate efficiently at 48 kilohertz. And when you increase the frequency in a circuit, the size of the capacitors, the size of the inductors, the size of the transformers gets minimized. So you can see the difference in the size. So what you pay more in semiconductor, you make up because of the other bill of materials becomes cheaper due to the smaller size. So price parity can be achieved with silicon at the system level, not at the chip level. The chip will be more expensive in silicon carbide, but at the system level, because you have reduced mass and volume of magnetic components, as you see here, and because of the great thermal conductivity, you simplify the thermal management. So for mass commercialization, for mass acceptance, the cost savings at the system level must outweigh the higher cost of manufacturing silicon carbide devices. And by using silicon carbide, because of the better efficiency, you have fewer lower emissions, which is very good for our planet. Okay, so let's look at some of the specific processes for silicon carbide that are different than silicon. So this is a planar MOSFET that you see here, which means that the channel is right here. It's planar. And there's another version of, and these are the resistance elements. The points of high electric field are shown here in this area, but they're very manageable for the planar MOSFET. And there's also the trench MOSFET. In the case of the trench MOSFET, it's a device where the channel is vertical. Remember, it was lateral here. The channel in the planar MOSFET, it's vertical right here. And these are the different resistance elements. And you can see this JFET resistance area right here, which is kind of a bottleneck between the two P wells. It's a narrow area of high resistance. And this is the JFET resistance as it is known. There is no JFET resistance in the case of the trench. So you reduce the resistance in the case of the trench. And because you have a vertical channel, the device becomes smaller. It doesn't have this planar channel that makes it extend more. So low resistance because you don't have the JFET, and also the fact that it's a smaller device, and it so happens that the mobility in silicon carbide is anisotropic, and the vertical mobility here, so having a vertical channel, you have vertical mobility here, the mobility is 20% higher. The problem, of course, with the trench MOSFET, because nothing in life is free, is that it has these areas at the corner of the gate oxide that are very prone to breakdown because of the very high electric field concentration in this area. So the JFET region that contributes to the resistance is eliminated in the trench MOSFET, and the MOS mobility in the vertical direction is higher, and you have a smaller device extent, which means you get more devices per wafer, and all those reduce the cost. The drawback, of course, is that in the trench MOSFET, the blocking voltage capability can be lower because you have the high electric field at these corners, so you're not going to get to the full capability of the drift layer unless you do certain design modifications. And again, this is the planar, the trench MOSFET that we talked about that has these problems at the corners of the gate oxide. And Rome is using a trench MOSFET, so it has the gate, but it also has two dummy gates on either side of every gate. So that's the way they alleviate the high electric field in this corner, together, of course, with rounding the corner right here. That's very important to round the corner right here. And Infineon is also doing a trench MOSFET, and their design is shown here. So for every gate, there's this channel where there's conduction, but the other side, the channel is not used. They're using this P plus implanted area to basically alleviate the electric field buildup that happens in this corner. Okay, so these are the two major designs for the trench MOSFET from two of the largest companies in the world. So let's look at the planar MOSFETs and look at the contributions of resistance. And this graph gives you the resistance of the device versus its blocking capability. So if you make a device that blocks 1000 volts, obviously it's got a thinner drift layer to do so, and the resistance is shown here. If you make the device to block 10,000 volts, then the resistance is all the way up here as expected. So this is the resistance of the drift layer that holds the high voltage. Other elements of resistance are the channel resistance from this area right here. There's the JFET resistance that's shown right here, and there's the resistance of the source and all the contacts that's shown here. And very importantly, there's the channel resistance. Okay, so if you're designing a 1200 volt device, which is a very common high volume device because of power supplies and because of the 800 volt electric vehicles, you can see here this is your total resistance, and the biggest contributor is the channel resistance, and the second biggest contributor is the substrate resistance, and then there's the resistance of the layer that blocks the 1200 volts. Okay, as you can see, the channel resistance, the resistance of the substrate, the resistance of the JFET, as well as the resistance of the contacts is independent of the breakdown voltage. It's really the drift layer resistance, the resistance of this thick layer that holds the high voltage, that depends on the voltage, because you go up in voltage, this layer needs to become thicker and lighter doped. And of course, another observation is that once you exceed about 3000 volts, okay, the total resistance of your silicon carbide device is basically the resistance of the drift layer, right? You see how this total resistance starts to converge with the drift resistance. So for the 1200 volt device that are very important, we have the substrate that's very high and the channel. And if you look at this graph right here, it shows a substrate of 350 microns, which is the substrate of the which is the thickness of the substrate as you buy it from the market. But then you can thin the substrate to 100 micron. Now you see how the substrate resistance has dropped significantly. So in order to reduce the substrate resistance within the substrate, and we have the channel resistance, and the way to reduce, of course, the channel resistance, as I mentioned before, is to go into a trench MOSFET, which in theory can lower the channel resistance, although because of the trade-off of the electric field here and the tricks you need to do to take care of that, you know, it's not a clear win. And the way you thin the substrate, you put the wafer in this grinding wheel, and then you use the grinding wheel and you take the wafer from 350 microns, which is how you buy it, down to 100 microns to reduce the substrate resistance. Okay, so how do you do the etching? There is commercial reactive ion etch systems that were developed for silicon, and they're fine to etch silicon carbide. There are different chemistries that can be used to do silicon carbide etch, with the SF6 being a very popular one. The etching rates are relatively low because silicon carbide is a very hard material, so it's very difficult to etch it down. Oxygen and argon are used to enhance the removal of carbon atoms to promote the etching. You have to adjust the pressure, the gas flows, and the RF power. Inductive coupled plasma RIE can help you increase the etch rate, much like in silicon. And these are some of the mask materials. You can see that if you use resist, that's commonly used in silicon, the selectivity is very, very low. So you eat away the resist layer at twice the rate that you etch the silicon carbide. So therefore, oxide is a good solution with a chlorine-based RIE. It can give you a selectivity anywhere between 4 to 15. And then you can use aluminum and nickel as metals, although metals are not preferable in a manufacturing environment. Let's look at the process now to do the etch. You come and deposit the mask material, whether that's an oxide or a metal mask, and then you put the resist. The next step is to go to the lithography equipment and expose the resist and then develop it. So the areas that got exposed, if the resist is positive, then these areas dissolve away, and now you got your pattern resist here and the mask material, which typically is an oxide, and you come and etch away the masking material, okay, and now you're at the silicon carbide surface, and you get rid of the resist, and it's really this hard mask here that's going to be used to etch down in the areas that are open to do the etch, okay? So to do the etch, you need to do one photolithography step. You need a hard mask, typically an oxide mask. And it's also the same way that you can form a metal pattern. Instead of an oxide, if you use a metal here, you go through this process of etching down the metal mask, you can end up with a metal pattern, whatever metal pattern is desirable for your wafer. Okay. So where do we need this? The etch of the silicon carbide is to create the trench, so you can have the trench MOSFET. You can make the gate of the trench MOSFET. So as I mentioned before, you use an oxide mask, and after you define the oxide mask, you come with the RIE and etch down the silicon carbide. And some of the desirable characteristics, you want a flat bottom with rounded corners to basically reduce the electric field crowding at the corner. And you want vertical sidewalls of good quality. You want to minimize the roughness. Depth is anywhere between 1 to 2 microns. The width is 0.5 to 1.5 microns. And here's an example of a trench. You see the oxide here, that's the hard mask, the silicon carbide below. But this is not an optimized etch. You get these micro trench features right here, highly undesirable, and it's not very vertical. But if you spend the time and work with the equipment manufacturer, you can get something that looks like this. Now you can see here, the sidewall is vertical. The roughness on this sidewall is very low, and you're getting this nice rounded corner for the trench, which will help you minimize the electric field buildup. Okay, so that's how you do the trench in silicon carbide. And this is an example of a trench surface. This is something that I trenched, in the mid 2000s, and you can see the silicon carbide pillars. And I use an aluminum mask, and I use the aluminum mask protected this area, so I was able to make these trenches right here. So this is an example using a chrome aluminum mask, and this is an example right here from Purdue University where an oxide mask was used to do the trenches. Okay, ion implantation, that's another area where silicon carbide differs from silicon, and you need to develop specific processes. As I mentioned at the beginning, diffusion, which is a temperature effect to spread the dopant atoms, does not work in silicon carbide. So therefore, we're using ion implantation. It's performed at high temperatures. You need to perform it at high temperatures in order to keep the quality of the crystal. Because of the hardness of silicon carbide, the implantation is at very high energy. So you're really bombarding the wafer, and that can be a problem. You can do room temperature implantation as long as you only require low implant doses. Doping densities for ohmic contact formation, you need to have very highly doping contacts in silicon carbide in order to put down the metal and create the ohmic contact. So the doping densities are very, very high for that. You can use Monte Carlo simulations to basically simulate your implantation, get some idea of how to design it. And after you're done with the implantation, the wafer basically has lost its crystallinity, and you also need to activate the implant species, the dopants. So you need to do an anneal, typically done at 17,800 degrees in order to get the activation and recrystallize the wafer. And you can put test structures to basically measure different aspects of your implantation and improve the process. And the implanted profiles are retained when you do that 17,800 degree anneal, because as I mentioned before, there's very low diffusion in silicon carbide unless you go to extremely high temperatures. And we need to have shallow dopant species. So for the P+, aluminum is best because it's relatively shallow compared to boron. And in the case of the N+ doping, you have a shallow level for nitrogen as well as phosphorus. They're relatively close. Boron is not typically used because it's not very shallow, and also it has a lot of defects, and that stops you from getting a low resistivity contact. So it's almost exclusively aluminum for the P+ in silicon carbide. And just to give you an idea about the room temperature implantation. So if you do a room temperature implantation, if you do the implantation without heating the wafer, you can see that basically when you anneal the wafer, okay, then you get almost 100% activation as long as your dose is low. So these results here are for low dose. If your dose is low, below 10 to the 15th, then if you do an implantation at room temperature, you don't use heat, then you can get very good activation of the dopants. And this here, this graph right here shows the electrical activation for P+ implantation for the two available species, the aluminum and the boron. And you can see that if you do room temperature implantation at low dose, if you anneal at about 1700 degrees, the aluminum will activate almost all of the dopants. But in the case of boron, you have to go to higher temperature to get the dopants to activate. So therefore, aluminum is the preferred species for implant for P+. And then let's talk about the high dose right now. So if you look at here at the implant dose, and this basically gives you the roughness of the implantation. If you have room temperature implantation and you do an anneal, okay, if you basically do not anneal, you have high dose room temperature and you do not anneal, you can see that once you exceed to the 10 to the 15th, basically there's a lot of roughness. Okay, so the wafer becomes garbage. And even when you do the anneal at 1600 degrees, once you exceed about 310 to the 15th, then the roughness goes up, and then the wafer is not usable anymore. And if you do 500 degree implantation, so the implantation right now is not at room temperature, it's at 500 degrees, you can see that if you do room implantation, even if you go to high implant dose, if you anneal, you still get a very good surface and you activate the dopant. So once we exceed 310 to the 15th dose, room temperature implantation does not work anymore. And high dose heated implantation damage, any damage that happens because of the high dose of the heated implantation, you can recover during the annealing. And you can see here that you can implant 10 to the 16th centimeter -2, and this is without the anneal, and this is with the anneal. Once you do the anneal at high temperature, you get a very high quality implanted space. And the high temperature annealing at 1600 degrees or higher is required for all implant doses. So just to give you an example here, you can see the 4/8 silicon carbide, as I mentioned, is in the UV range. And this is a sample, a quarter sample before implantation. And this is what it looks like after 400 degree heated implantation. Basically, the crystal turns into glass, okay? So then you go and do an anneal, typically 17 to 800 degrees. And this is an anneal that was done without using a cap layer for the wafer. And you can see the quality is very, very poor. And here's the situation where you did use a cap layer and you get a very good surface. So the bottom line is there are different cap layers that you can use. What I have found works best is to use, a graphene type of layer. So all you need to do is put resist on your wafer, and then when you put it to 1800 degrees or 1700 degrees, the resist will basically become carbon. It will carbonize. So you will have graphene, and that will be a carbon protective layer. So you can see here when there was no protective layer, basically the surface looks very poor because the silicon desorbs and migrates from the surface at a faster pace than carbon. Once you cover it with a carbon layer, then you don't have this desorption problem, and the wafer looks good. And you can see here the roughness with the carbon cap. Even at high doses, the roughness is relatively low. But then if you don't use a cap layer, then you get a very rough surface. So the bottom line is, when you do the implantation anneal in silicon carbide, you need a cap layer on your wafer. And this is another example where you see that there is no cap layer, and you can see what the surface looks like. It's relatively poor. And then here's the situation where you use a cap layer. So basically, the high temperature anneal in silicon carbide requires a cap layer, and carbon is the best to use. Okay, now this is an example of P plus implantation. This area region, you see there's a small implant straggle that you need to take care of. And the issue is that when you do the implantation, unfortunately, you can introduce defects. So there are defects that are introduced during the implantation process. And I mentioned some of these defects here. One of the worst ones is the basal plane dislocations, because those are detrimental to the device. So when you do the implantation, you need to develop the process in a way that you minimize the defect. If you look at this device here, this is basically the gate to drain junction. Okay, and once you turn this junction on, which activates the basal plane dislocations, you go from here to here. So you went from 0.12 to about 0.2. So, about 6 times lower current. Okay, so there's a lot of degradation. And this is the on-state current running through this JFET. And you can see before the degradation, it's this black line. Because of the basal plane dislocations in the device, when you turn the junction on in the device, it degrades. Okay, so luckily, with respect to basal plane dislocations, when we get wafers that are 4-degree cutoff from the boule, which is the standard practice in silicon carbide, 95% of the basal plane dislocations in the substrate will propagate as benign threading edge dislocations in the epitaxy. So that greatly reduces the number of basal plane dislocations that are present in your epitaxial layers. Okay, let's look at metal patterning and ohmic contact formation. And I showed the process before where you put metal down and then you use resist to pattern the metal and etch the metal. And that's how you create an etched metal pattern on the wafer. And as I mentioned before, putting metal down on a silicon carbide wafer will not give you a low resistivity ohmic contact that's desirable. It will give you a Schottky contact. You can see here, this has a Schottky signature. And this here is an ohmic contact. And this is because of the barrier height between silicon carbide that has a wide band gap and the metal interface. So to form a low resistivity semiconductor metal ohmic contact in silicon carbide, you need to basically follow some steps. You need to put down the metal and then anneal at 900 to 1000 degrees. And you can do that either in a rapid thermal annealer or you can do that with a laser annealer. And you need a very heavily doped silicon carbide surface at the place where you're going to form your ohmic contacts. And nickel is commonly used to form N-type silicon carbide metal contacts. And for the P-type metal contacts, the best one is the aluminum titanium alloy. And ohmic contact formation is more difficult in the case of P silicon carbide because of the higher Schottky barrier, because you're in the valence band. And to reduce production times, you basically want to do the ohmic contact for the N and the P at the same time. Do them simultaneously, and in that case, you typically use nickel. So let's look at some of the things I mentioned before. If you look at this graph here, it shows the resistivity as a function of the anneal temperature, and you can see if you don't anneal, or if you anneal at 900 degrees, the resistivity is relatively high. By the time you get to 1,000 degrees and a little more, your resistivity goes down, and this is for nickel to form N-type on the N-type surface. If you look at this one here, this is annealing at 1,000 degrees, and you can see that the higher the density, the doping of the area where you're forming the contact, the lower the resistance. So to form ohmic contacts, you need to dope at 10 to the 19th and anneal at 1,000 degrees to be at this point. If your doping is at a lower level, then your ohmic contact is very resistive, which is undesirable. And this one here shows the case for the P-type. This was the N-type, this is the P-type. And you can see here that in the case of the P-type, even for high densities, right, high doping densities, you're at 10 to the -5 or so. So you're an order of magnitude less or more resistive compared to the N silicon carbide contact. So when you're doing both NP silicon carbide contacts, you typically put nickel down, and that makes things even worse because you're not using the optimal aluminum tie for the P+. And an example of ohmic contact, this is basically the surface of the wafer. This is the source area, and this here is the gate, the implanted gate area. And I've put a layer of nickel here, so this is coated with nickel. And then I do a silicide, and when I do the silicide at about 950 degrees for about 1.5 minutes, you see how I go from this picture to this picture here. Now what's created here is silicide, and after you do the silicide, you put a thick metal layer, and that's your interconnect metallization. And as I mentioned before, for the P gate, you're going to be close to the 10 to the -5. The thickness of nickel to do the ohmic contact is about 50 to 100 nanometers. And these are older experiments that I've done. Like you can see in this experiment here, where the source is not encased in a dielectric, I get a lot of metal lines, and those can short the device. So you need to develop an ohmic contact process for silicon carbide. And the rapid thermal anneal, it's done with a halogen lamp. It can go up to 1,300 degrees, and basically you expose the whole wafer to this flash of 1,300 degree light that can last anywhere up to 2 minutes, and you do one wafer at a time. If you do the laser anneal, then you're using a laser to scan the whole surface of the wafer. You go to 2,000 degrees or more, pulse laser are used. It's a very fast process, and you scan the whole wafer. And you can see the advantage of the laser anneal that you see right here. You're only heating up the area where you're creating the silicide. So this area of the wafer is heated up. The rest of the wafer stays at lower temperature. And actually, you do step by step as you scan across the wafer to do the silicide. The other side of the wafer stays below 100 degrees, even though this localized area gets about 2,000 degrees to form the silicide. So the way you make devices, a common way to make devices, is you process the device till the end, and then when you get to the end, you want to thin the substrate to reduce the resistance. You don't thin the substrate at the very beginning, because if you take the 350 micron substrate and you make it a 100 micron substrate at the very beginning, then during processing, the wafer is going to crack. That's way too thin for mechanical stability. So what you do is you process the wafer fully, and when you get to the very end, you put resist at the top of the wafer, you flip the wafer over, and that's when you go and thin the substrate. And after you thin the substrate, you're using this laser anneal to create silicide. You put nickel and do this laser anneal to create silicide at the back of the wafer, which serves as the drain. And the reason why you use this laser anneal is because the wafer is now thin, the whole front surface is fully processed, and if you put it in a rapid thermal annealing, you will basically melt the ohmic contacts on the front side. If you use the laser anneal in the back, you're going to raise the temperature locally, but the front of the wafer will be below 100 degrees, which is not a problem. Okay, let's look at the gate oxide. This is for silicon, and you can see the maximum value of the gate oxide is 60% of the bulk, and this is for the inversion layer between the silicon carbide and the oxide layer. And you can see in silicon it varies between 30 to 60%, so you get 30 to 60% of the bulk value in silicon. When you do the gate oxide in silicon carbide, number one, you have to do a nitrous anneal to increase the mobility, but then even then the mobility at the two ends is somewhere between 5% to 3%. So in silicon, you retain anywhere between 30 to 60% of the bulk mobility. In the case of that interface layer in silicon carbide, the mobility is only 5 to 3%. So the question is, why is the inversion mobility in silicon carbide so poor? Okay, and the answer is because you have a very poor quality silicon carbide oxide interface. It's got a lot of surface roughness, which is not the biggest of problems, and that's something that we're treating well now. We can basically reduce the roughness, but then you have all these carbon to carbon, silicon to silicon dangling bonds that create traps. So it's basically you have a lot of traps in the silicon carbide oxide interface, and that basically degrades the mobility and causes threshold voltage instability. So what is threshold voltage instability? You can see here that this layer right here has a lot of silicon to silicon bonds. It's got carbon-carbon bonds. It's got dangling bonds. And then you have these mobile ions. And all these things contribute to trapping electrons and reducing the mobility. And threshold voltage instability means that if you bias the device in a certain way, you increase the conduction losses because you increase the threshold voltage. If you bias it in the opposite way, then the threshold voltage gets reduced, and that's very dangerous because now your threshold voltage is so low that an unintentional, like a noise, a spike, can actually unintentionally turn on the device. So the standard gate thermal oxidation process, you start here. You insert the sample in flowing oxide to grow a thin oxide layer and prevent loss of silicon from the surface. Then you raise the temperature to about 1175 and do a dry oxidation or wet oxidation to form the oxide. The next step is to do an argon anneal to remove carbon from the bulk oxide. And then you want to basically do a low temperature oxidation to minimize the transition layer. And finally, and very importantly, you're doing a post-oxidation anneal in nitric oxide to passivate the interface states. And this is the standard process. It's really this nitric oxide that has increased the mobility to the point where we could make useful devices. It was actually a breakthrough, but nevertheless, the mobility is very low. So there's one technique that's kind of new from the group of Professor Kimoto in Japan, where he basically does a hydrogen pre-etch to reduce surface roughness. And then instead of doing a thermal oxidation, he deposits an oxide at low temperatures to reduce the interface traps. And then he comes and does the nitridation anneal. So if we look at his results, the interface states get reduced by half. And this is shown in the graph right here. You can see the standard process where we have the oxide and the thermal oxide and do the NO treatment. This is the number of traps, and this is a log scale. And with the new process, you can see that you're cutting the number of traps by 2.5 times. And also, if you look at the mobility, this is the mobility here of the standard oxide process, and this is the mobility of the electrons. When you use this improved process, you increase the mobility by 2 times. So that's a very promising result that is at the experimental stage at this point. Okay, so to summarize my talk, I talked about the steps that you need to take to fabricate silicon in a silicon carbide fab, and basically the process that you need to develop that are specialized and specific to silicon carbide. So they don't exist in silicon. And we talked about the etch, where you have to do dry etching, typically using an oxide mask. We talked about the implantation, the doping, which is basically done with high temperature implantation and then an anneal step at 1700 degrees or above with a cap layer to protect the surface. We talked about the ohmic contact formation that can be done with a rapid thermal anneal if you're at the stage of making the contacts in the front of the wafer, or do a laser anneal to form the ohmic contact in the back of the wafer at the very end of the process. And then we talked about the issues with the gate oxide. The silicon carbide oxide surface is of very low quality, has a lot of traps. You do an nitric oxide anneal in order to improve the mobility and passivate the interface traps. And as I mentioned, there's a lot of work in this area and new experimental methods to improve the gate oxide. And with that, I want to thank you for your attention. And I'm here to take any questions you might have.
Thank you, sir, for the wonderful informative, especially the devices. It's helpful and we appreciate it. So, sir, before we
Mohammed, your voice is not very clear.
So,
Go ahead, please.
yes, sir. So, sir, the first question was that you said that so like it is 50 millimeter for formation.
I'm sorry, I cannot hear you well. You're breaking up. Is there an area where the questions are written down?
Hi, Victor, can you hear me?
Yes, I can hear you very well. Yes, yes.
Yes, so my students have been, contacting you over the long time, to organize this talk. Like, it would have been really nice had you been here in our institute at IIT Indore in India. But we're very, very much thankful to you that you could take out your precious time, first of all, having, good conversations with my PhD students. Over the several email conversations I could see, and now you are giving a really nice talk. And I think many students, and the young researchers and junior faculty members, not only of our institute and many institutes across India and across globe, who are working in the domain of power electronics mainly, and probably working towards, semiconductors like silicon carbide or maybe diamond, like who had been pursuing this type of research work, and they are very much beneficial to you. So I would like to, give you our heartfelt thanks to take out, your precious time. I'll be just handling over to our student coordinators because right now they're facing some internet issues. So I hope
Okay.
now that issue is resolved. So I'm handing over to my student who can take this session further to brief question and answer session. Thank you so much.
Very good. I was in India for 3 weeks in December, and I went to several places across India. I started in IIT Bombay. I went to Surat. I went to Karnataka, to Bangalore. So it was a great experience. And maybe next time, if I can make it to India, I'll make a point of visiting your institute.
Absolutely. So you had been to ISC Bangalore, that is the southern part of India. IIT Bombay, you mentioned, that is the western part of India.
Yes.
And we are at the central, we are at the heart of, we can say India. So next
Okay,
time, if you would like to make any plans, please let me know, let us know, and would be, loving to be your host at IIT Indore and organize a beautiful session for you to interact with all of us.
Absolutely. Thank you. Thank you. I'll make sure that we get in touch next time I'm able to. I travel to India.
Sure, sure,
So,
definitely.
re-
Now I
ready
will
for your
continue.
questions?
Yes. So
Oh,
students, please.
yes. Thank you, yes, sir. Thank you, Professor Saiwal, for helping us. And sir, I have two questions regarding the ohmic contact formation.
Hmm.
So, first is you have mentioned that the thickness of nickel should be 50 to 100 nanometer for a good ohmic contact. So, sir, is there any reason for that? And so I will also ask my second question. So, you have mentioned that 2 minutes of annealing time is enough for ohmic contact formation. So, I know that lower it might not be, but what are the consequences of going for higher annealing time? Means by chance, for the sake of experiment.
Yeah, yeah. So, it also depends on your equipment, right? What I have found is anywhere between 50 to 100 nanometers is is enough to make contact with the silicon carbide underneath and form the nickel silicide. If you put a thicker layer, the danger is that some of that nickel that you're putting down will not react with the silicon carbide underneath to form a silicide layer, and then that will create problems when you come down with the aluminum layer. So, in a lot of cases, if you put more nickel, you have unreacted nickel that you need to basically get rid of. And that's a very painful process. So, if you're experimenting with this, I would start with this range right here and see what type of results I get. With respect to the rapid thermal annealing, I can send you a recipe that I tried and it worked well. I think it was 325 or 350 for about a minute and a half. So you have the whole wafer that basically goes into the chamber, and it's really a flash that creates that high temperature for a very small period of time, and that is sufficient to create the silicide. Now, if you leave it longer, when it comes to manufacturing, anything that takes a longer time is more costly, right? There's more labor. So I have found that that's the right amount of time to form silicide with the rapid thermal annealing method. Okay, if so, if you have when you do the front right along the process, you do the RTA, you create the silicide in the front layer, you do all the ohmic contacts in the front, but then the drain in a vertical device is in the back of the wafer. So that you do at the very end. So when you do that first nickel silicide, you only have metal on the front of the wafer, not the back, because remember, we want to thin the back of the wafer, we want to thin the substrate to reduce the resistance. So you do the front of the wafer along the process to form an ohmic contacts in the front, and then at the very end, you put resist in the front, you flip the wafer over, and the resist is to protect the front surface, and you thin the substrate in the back. You drop it from 350, you take it down to about 100 micron, and then at that point, you got the surface in the back, you put a nickel layer, just blanket nickel deposition, and then you come with the laser anneal. Because if at that point you do an RTA, then the whole wafer will get to 1300 degrees and you will destroy all the ohmic contacts you made in the front. Okay, so that's where the laser anneal comes in. If you follow that flow, you will not be able to make competitive devices if you don't thin the substrate. So when it comes to devices that are up to 1700 volts, you need to thin the substrate. Now, once you exceed 1700 volts and you go to 3.3 kV, 6.5 kV, 10 kV, the thickness of the layer that holds that high voltage is basically the majority of the resistance. So you can afford to have a thicker substrate. But for the competitive 600 volt devices that go to 400 volt battery vehicles, for the 1200 volt devices that are used for the 800 volt vehicles, for the 1700 volt devices that are used for the heavy duty vehicles, and for all the power supply applications and motor drive applications, which are at the 600 volt device level, for all of that, you need to thin the substrate. Okay, so those are the two processes. You use the RTA because it covers the whole wafer in a single event. So you do the RTA for the ohmic contacts in the front, and then when you get to the back, you thin the substrate, you put the nickel down, and to get the nickel to react with the silicon carbide material in the back, you use the laser anneal to keep the temperature at 100 degrees in the front. It's going to go to about 2000 in the back, but the front will see very low temperature.
Thank you so much, sir.
Hello.
Yes.
Yeah.
You can ask questions to Prof.
Hi, Professor Victor. Thank you for the wonderful presentation. I have a couple of questions. You mentioned 6.5 kV and 10 kV SiC devices. What is the typical epi thickness for that? And I mean, what are the defects associated with that? Is it commercially practical,
Yeah,
realizable?
Pavan, first of all, could you please introduce yourself? Because your camera
Okay.
is not also switched on. Please introduce brief details about yourself.
Okay, sure. I am Pawan. I work with the Tata Electronics as a principal engineer there, and so my area of interest is wideband gap and silicon power devices too. And yeah, so I have a couple of questions with respect to presentation. So these are like when it comes to 6.5 kV and 10 kV SiC devices, these are like SiC MOSFETs. And what are the AP defects associated with that? Like a substrate can handle the higher AP thickness. Yeah.
Yes. So there's a formula that gives you the optimal thickness and doping of the drift layer for every voltage level. And I can send you that information since you're interested in that. To make a 6.5 kV device, you need about 60 microns of drift layer thickness at the 10 to the 14th level. To make a 10 kV device, you need a 95 micron thickness at the low 10 to the 14th doping level. Okay? And this thickness and doping levels that I mentioned are basically the optimal when you solve the equations, right? So that's well known, and I can give you those values. Now, the hardest thing about making these 6.5 and 10 kV devices, and I made my first 10 kV devices back in 2006, 2007, because those devices have huge military applications, and I had contracts with the United States Navy and the Army, and I was making high voltage devices. These high voltage devices, 10 kV devices, go to direct energy weapons like electromagnetic weapons. They go to the electromagnetic catapult, which is basically assisting aircraft to take off from aircraft carriers. They go into what's known as the electromagnetic shield, which creates an electromagnetic protection on military vehicles from incoming projectiles. Okay. And then, of course, there are the big applications. Fast charging stations is a huge one. And of course, grid modernization, basically tying the grid to the renewable energy. You need to condition the power. You need 10 kV devices. Okay. So 6.5 and 10 kV devices. The hardest thing you have to solve is making that thick epi. To make the epi very thick, right? 60 microns and even more, 95 microns, the wafer has to stay in the chamber for a much longer time compared to making the 4 micron epi for 600 volts or the 8 to 10 micron epi for the 1200 volts. The fact that the wafer stays in the chamber for a long time for the epi layer to grow, okay, has the danger of fallout. So there is particles that are deposited on the chamber as you grow, and those can fall on your wafer during your growth, and that will of course destroy your layer. So the number one problem that we need to basically work on and fix is getting thick epitaxial layers of very low doping in a way that they're of high quality, meaning there's no particles that are falling. Now, the second thing is the basal plane dislocations that I mentioned before. They will have a small impact on a 600 volt or a 1200 volt device, but basal plane dislocations, if they're present in the epitaxial layer for a 6.5 or 10 kV device, and I can send you, publications that I have on that, that will really degrade the device pretty badly. Okay. So the other thing is we need to have clean epitaxial layers that do not have basal plane dislocations. And remember, basal plane dislocations can come from the material, the epi layer that you have, they propagate from the substrate, but also basal plane dislocations can be generated during the implantation process, depending on how you do the implantation. So there is a lot of work and a lot of reward in making these high voltage devices. And the biggest aspect that you have to tackle is making a good quality, thick epitaxial layer. That's the number one. Now, once you have a good layer, when it comes to making the actual device, things I would say are even easier than the 600 volt and 1200 volt device. Because number one, you don't need to worry about the substrate. You don't need to thin the substrate because all of the resistance of a 10 kV device, 99 plus percent, comes from the thick drift layer. So you don't need to worry about the substrate, and you don't need to worry about minimizing the channel resistance. Okay. And that's very important because in a planar device, and even in a trench device, when you try to reduce the length of the channel to minimize the channel resistance, the device basically does not hold well when it comes to short circuit events. So you're compromising short circuit performance with lower resistance by making the channel thinner. You don't have to make that compromise in 10 kV devices because, again, the resistance of the channel is negligible compared to the resistance of that thick drift layer. So the number one thing we need to do is to create good, thick epitaxy. And there are a ton of applications for that. And why stop at 10 kV? You can do a 140 micron layer and get a 15 kV device. Only now it needs to be an IGBT. So there's extra work there to basically engineer the lifetimes of the electrons and the holes, right? IGBT is a bipolar device. You have two types of carriers. So there's a lot of benefit from being able to make a thick epi device with a clean epitaxial layer. So we were making 10 kV devices in 2006, 2007, but it turns out that the big application that put silicon carbide on the map were electric vehicles. And electric vehicles initially needed only 600 volt devices, and for the higher class of electric vehicles, it was 1200 volt devices. So all the effort, all my friends that were making high voltage devices, even I was making high voltage devices, we all stopped, and companies started assigning us to work on low voltage devices because that's where the market was. That's where the money to be made was. Remember, I showed a graph, and I'll try to get to that. I don't know if you can see it on my screen, but if you look here, 75% and more of the silicon carbide devices are going to automotive and mobility. So that's electric motorcycles, electric vehicles, rail, and the rest, the biggest chunk is industrial, which is power supplies and motor drives. So automotive is a really big one. And because automotive doesn't require high voltage devices, no attention was paid to that thick epi. Now, where everybody's looking at grid modernization and tying grid to renewables, there's a lot of work happening at high voltage as well. But if you are interested in high voltage 10 kV MOSFETs and 10 kV JFETs, all that stuff was made between 2005 and 2010 by several players, and then it was kind of put to sleep after that, and it's woken up recently when people are paying attention to high voltage devices.
Oh, yeah, thank you, Professor. I have a couple of questions to add to that. In terms of, yeah, as according to JFET, according to trench MOSFET, JFET is eliminated with the structure, but with the commercial structures from ROM and Infineon, JFET is introduced, right? So, do we need to consider now JFET effect in the trench MOSFET with the commercial structures?
So you have the trench MOSFET that's coming from Rome and Infineon, and these are two giants, especially Infineon when it comes to silicon carbide devices. They're using trench in the case of Infineon because they have a platform that makes trench, easy to make. And even when you get to 3.3 kV and beyond, where the trench is not really helping you, because remember the reason behind the trench is to reduce the channel resistance, right? Because you have vertical conduction with higher mobility, and because it's vertical, you're reducing the size of the device becomes smaller. um, if you look at Wolfspeed and if you look at ST Microelectronics, and ST Microelectronics was the company that basically inserted its MOSFETs in Teslas, right? So huge market, one of the big ones that won that massive contract. There's more than 230 million MOSFETs in Teslas today. Okay, they go with the planar MOSFET, so it's not clear that one wins over the other. Yes, if you use if you have and let me show the right slide. If you have a trench MOSFET, right, you have this vertical conduction, higher mobility, you have smaller area device. These are good things, but because you have this buildup of electric field in the corner that you need to take care of, then you got to come up with devices that basically either have this dummy type of edges which take space on the wafer, or in the case of Infineon, you're losing conduction over half of the gate. Instead of having conduction here, um, as well as right here on both sides of the gate, um, you only have conduction on one side. So there's no clear win for the trench MOSFET in the low voltage area. Wolfspeed and ST are doing planar, Roman Infineon are doing the trench, and the performance is comparable. Otherwise, the market would have shifted into the trench if the trench was superior device. So both are viable. But again, once you exceed 1.7 kV, the trench doesn't really help you. You're reducing channel resistance, but it's negligible compared to the thick drift layer resistance. So it doesn't really help you in that case. But yes, these are the consideration. And the JFET region that we mentioned is this area right here. You want to do this. I don't know if you can see my drawing, my slide here.
I can see that.
Okay, so you have these two P wells. You see those two P wells right here? The reason why you have these P wells is if there's a high voltage, the depletion region of this P well expands, and these P wells expand in depletion and protect the gate oxide from the high electric field. That's why you have those two P wells. Unfortunately, the fact that you have those two wells, it creates a bottleneck area that basically provides, increases the resistance by this JFET resistance. And that's, the goal behind the trench was really to eliminate this JFET resistance. Okay, but because of the trench having this corner issue, it's not a clear win. It's not a clear win, and you can try devices from Rome, you can try device from Infineon, and you can take device from ST and Wolfspeed and compare. And people have done that work, and there's a ton of publications comparing trench versus planar devices. There's no clear win. It really depends on what your platform is, what your fab capabilities, or your design, how your design works. That's really what it is. It's not one or the other, or one being better than the other.
Okay, and one more question is like we found the contact on the body and N plus source, so we can use the same metal for the both, or like I mean, so it's a P plus body and N plus source, right?
Hello,
When you are
Pawan.
forming a contact.
Hello,
Yeah.
Pawan.
So when you make the ohmic contact, and let me get to that section. When you form the ohmic contact, right? In the case of the N type, so both for N type or P type ohmic contacts, the silicon carbide underneath the area of the contact, underneath the area where you put the metal, needs to be doped to the 10 to the 19th. It should be doped as much as possible, and your implantation anneals should activate 95% or more of the dopant. So assume you have high doped area, and now it's an N area, and you come down with nickel, and you do the silicide. You can see here that the temperature of the RTA, if you do an RTA at 900 degrees, your resistance is pretty high. When you get to 1100, your resistance becomes low. Okay, and of course, the higher the doping density of the layer, the silicon carbide underneath, the lower the resistance. Now, in the case of the N silicon carbide, nickel is the right metal. Nickel is the metal that will give you the best ohmic contact low resistance. In the case of the P, aluminum tie is the best metal. And even with aluminum tie, that's the best metal, you're still in order of magnitude. You're 10 to the minus 6th in the N contact, you're 10 to the minus 5th in the P contact. Now, when I was making devices, if you do one step to do the N contacts with nickel, and you do a second fabrication step to deposit the aluminum tie and go through this photolithography process, number one, every level that you do has a yield loss. Number two, if you do the N and the P at the same time, then your process is self-aligned. The N and the P ohmic contacts fall at the right place and have the right relationship to each other. So it's highly preferred to do a single step for both N and P type ohmic contacts. Okay, so in that case, the best selection would be nickel. So by using nickel, you will get the optimal contact for the N. And by using nickel, unfortunately, it will be a little worse than what it would have been if you use aluminum tie. So look at this statement right here. If you do simultaneous nickel on N and P for contact formation, to do it in a single step, have the advantage, the labor and the yield advantage of doing one photolithography step. Unfortunately, you increase the P contact resistivity versus using aluminum tie, which would require a separate step. So again, Pavan, it's a trade-off. It's a trade-off. When I was making device, and I was making device for many years, the benefit of doing a single step for N and P basically was a better choice than doing two separate steps, so I could put aluminum tie in the case of the P. That was my experience.